All right. So in HPLC and normal chromatography, we're doing HPLC. There are two types: normal phase HPLC and reverse phase HPLC. In normal phase, it is just like normal liquid chromatography and TLC, where the stationary phase is polar. So stationary phase is the material packed inside. Yeah, that is polar, still polar. And if the stationary phase is polar, the solvent, which is mobile phase, passing through this will be non-polar. All right, that is normal phase HPLC. Of course, it works just like the TLC. If the normal phase HPLC is used, the polar material will stick to the stationary phase inside, and non-polar will elute first. All right. So if you're given a polar molecule, A is polar, same size, and B is non-polar, all right, and you're given normal phase chromatography, and you're asked which one comes out first, because it is normal phase, and because the inside stationary phase is polar, so the A polar will stick with it, will be making bonds with it, and will come out slow, and B will come out faster. So the first comes out, it will be non-polar. All right, reverse phase chromatography is quite common, is where the stationary phase inside is non-polar. They make it non-polar by attaching long carbon chain like C18 or something. And because this is non-polar inside, the solvent they use is quite polar, like ethanol or sometimes even water. So the mobile phase is polar and stationary phase is non-polar. So when the sample is injected, the non-polar parts of the sample will be slower, coming out slow. Why? Because it is making dispersion forces with the long carbon chain of the column, and the polar part will come out fast because the stationary phase is not recognizing. Yeah. And there are different sizes of this column. For example, if you see here, this is 5 micron, this is 1.7 micron. The one with smaller or finer powder, you can say that they have better resolution. You can see that if you want if you have machine, you can easily collect both A and B parts of this sample. But if you use this column, um, you'll collect some part pure, maybe A, and then this part will be mixture of A and B, and then C. So the smaller the size of the material packed inside, better it resolves. Yeah. Another important part of the HPLC theory is retention time. The time which the mixture, a part of the mixture spends inside the column is called retention time. Yeah. For example, if you have this, um, most probably this is the normal phase HPLC, because the ethanol most polar part is coming out late at 30 minutes or something, 30 minutes. Yeah. So this is retention time. So you've given retention time of ethanol is 30 minutes. So it stays inside the column for 30 minutes. And maltose, not all the peaks shown here, but some are coming at, you have to take draw a vertical line from the peak, maybe 12 minutes. So whenever you have a chromatogram like this, make sure to use ruler or scale to make sure exactly what is the retention time. For example, in this one, I'll first use a ruler to find out the middle of 8 and 16. Let's say this one, and that will be like 12. Just between 8 and 16 is 12. Then I have another middle of this one, and that would be 10. All right, and middle between 12 and 16 would be 14. And then it's easy to find out what is the retention time, and then you can match that retention time with the column. Yeah. So in HPLC, when you have to analyze this type of data, please make sure in the question they're asking you is reverse phase or the normal phase. In the reverse phase HPLC, the polar molecules come out first. Non-polar stays back. Why? Because the non-polar part is bonding with the non-polar material inside the column, so dispersion forces are more. And if it is normal phase chromatography, the polar molecules stay back, because in the normal phase the stationary phase is polar, so they stick to each other, and non-polar come out first. All right, and you have to find the retention time. You take the peak and use the scale and drop a vertical line and find this point. This is the retention time. Make sure to use the column to find. Now, if two compounds, they have same peak, like their height is same, let's say there's another one and let's say height is same, does that mean their concentration is same? No. The peak area is also important. Peak area means how wide in total, like height, width and everything. So it has more peak area, this one. So this is more like there is higher concentration of this peak is there. Other than polarity, the size of the molecule also matters. Like the larger molecule in reverse phase chromatography, for example, the larger molecules normally have longer carbon chain, which means that they can make more dispersion forces. So let's say if there's a column, all right, and it is reverse phase, which means that inside is non-polar, all right, non-polar material used, long carbon chains used. Now two molecules are injected, a mixture is injected with two per molecules with the same polarity, let's say. If the polarity is same but the size is different, one molecule is bigger in size, one is smaller in size, even if their polarity is same, both are non-polar, both polarity is same, but still the smaller will come out first. Why? Because again, the larger molecule tend to make more dispersion forces, more dispersion bonds. Yeah. So larger molecule will be more strongly attracted to a non-polar stationary phase and have higher retention time. All right. So outside the column, even if you think that they have same polarity, or all the groups are same, everything is same, but if one is larger molecule, it will make more dispersion forces and will come out slow. Volumetric analysis, another term used for titration. So titration could be acid-base titration, or it could be the redox titration. All right. Most common one is acid-base. Remember that in acid-base titration we use indicator. Why? Because normally acids and bases, they are colorless. We put some indicator in which has different color in acid and different color in base. So as soon as the end point reaches and acid change to base with one drop, it changes the color. So indicator are used in acid-base titration. In redox titration, we don't use indicator. Why? Because whatever metal ion is there, if it becomes, let's say if copper 2 becomes copper 1, it will change color. If chromium 7 becomes chromium 3, it will change color. So because the metals, as soon as they change their oxidation state, they tend to change their color as well. So we don't need indicator there. Now in acid-base titration, why we do that? Let's say if you are doing this reaction and you have a column, this is burette, yeah, this is burette, and you'll need a flask as well. Let's say in the flask you have acid, HCl for example, and you know it's 10 ml, all right, 10 ml, and maybe it's 0.1, no, concentration is unknown, and here use sodium hydroxide with known concentration 0.1 m, And during the titration, you will find after taking 3 titers or 3 titration, let's say you find out 20 ml was used, so 0.02 liter was used. So for sodium hydroxide, you already had the concentration. Now you have the V as well. Using C and V, you will find moles of this. All right. And for HCl, you only had volume 0.01 liter. But now using the mole ratio, you can find out how many moles of HCl used. So whatever moles you find here will be same for HCl because they are 1-to-1 ratio. And once you have moles of that, concentration is moles over volume in liter, so you'll find concentration of HCl. So titration is done to find concentration of an unknown. Yeah, look at this example. A 20 ml aliquot is what you take here in the flask, required to the addition of 27.3 ml of sodium carbonate. So sodium carbonate was in the burette here, and when we did titration, we find out that 27.9 ml was used to get to the end point. All right. Calculate the concentration of sulfuric acid. Now sulfuric acid, the only thing we have is volume. All right. Remember that these volume need to change to liters. So we have 0.02 liter of sulfuric acid and 0.02798 liters of sodium carbonate. All right. So we have only liters of this, and here we have these two things, so multiply them, you will find concentration. So N is equals to C times V. So when you multiply C and V, you got moles of sodium carbonate, which is this much. Now because the ratio is 1-to-1, whatever moles of sodium carbonate used here will be the same for H2SO4. So H2SO4 moles are also the same. So now you have moles here. You can use formula here, C is equals to N over V, and find concentration of H2SO4. All right. So this is the purpose of titration. There's another example, you can go over that. Now titration curve. Titration curve could be given like this or other way around, doesn't matter. I'll give you the other example. For example, if you have on the y-axis you have pH, and here you have volume of acid added. All right. Let's say in the flask here, let's say this is the burette, and in the flask, let's say you have sodium hydroxide, NaOH. NaOH is strong, so pH is here 14. All right, in the middle 7, here 0. And now as we add acid from the top, the titration curve starts from here because already we have pH 14. So you keep adding volume, so it goes like that, like that, like that. As soon as equivalence point come, 1 drop of acid will bring it down here. Change the pH. Why? Because that 1 drop is now after the neutralization point. All right. So this is called the acid-base titration curve because this is happening between strong acid and strong base. So that is called strong acid, strong base titration curve. Now you see 2 shoulders here. This is shoulder 1 and this is shoulder 2. Just in the middle of these 2 shoulders right here is the equivalence point. Equivalence point is when the moles of acid and base are equal. End point is when the indicator changes the color. Now this is the equivalence point. There are indicators. Indicators, they have their own pH. You want to pick an indicator which is closest to your equivalence point. Let's say your equivalence point is 7.1, say, and you pick an indicator which is working at pH 2 or 3 is strong. You have to pick an indicator which works in this range. All right. So that is called titration curve. Now in this case they have acid acid in the flask, so which means that the pH is already 2.5 in the flask, and from the burette you are adding some base, and most probably strong base. So acid looks weaker because it's not 1, it's like close to 4. So as soon as you started adding the sodium hydroxide from the burette, the pH slowly goes up, and at this point 1 drop of sodium hydroxide will take it up to 14. Now there's this shoulder and there's this shoulder. This in the middle, I put this star. That is like the equivalence point. So your indicator should be somewhere here. You can use basically any indicator which is between on the steepest area, any indicator in this range. But if you use, say, indicator at 4, some indicator which is working at 4, so the solution will change color before the equivalence point, well before the indicator. So that indicator is wrong. It will give you change in color, but not at equivalence point before that. Similarly, now in this one, this is strong acid. Why? Because the pH is like 1, and as soon as it changes the color, it gets to the 8. It means that this is the weak base. So now the equivalence point is somewhere at 5. So you need to use indicator in this steepest area. All right. Don't use any indicator which is working above 8. All right. Any indicator which is working in this area will not work for this titration. This is good example of strong acid and strong base. All right, it starts from maybe 1, and as soon as the end point reaches the change in color, it is going to 13 or 14. So strong acid, strong base. And just middle of this shoulder is right here, like maybe 7. So it has big range. You can use any indicator which is working in this area. All right. And this is very limited. Weak acid, weak base, you have to use some indicator which is like changing color at 6, 6.2 or 3. Look at this example here. Says here, choose an indicator which with the endpoint pH range lies on the steepest part. Yeah. So for example, in this example, you can, if you use methyl orange, all right, the equivalence point is here, all right, and methyl orange is very close to that. So methyl orange will change color. But if you use phenolphthalein for this titration, it will change color, but not at equivalent point. It will change color before that. So it will be wrong indicator, all right. But on the other hand, if you have this titration curve and the equivalence point is here, for this case, the phenolphthalein is good, but methyl orange is wrong. All right. If you use that one, you might not see color change at all. All right. So this is how titration curve are interpreted, and you should use the indicator carefully. This is another example. All right. So if there are 3 examples, if you use thymol blue, it will change color before the end point, and if you use alizarin yellow, it will change color well after the maybe indicator reached, and bromo thymol is best here maybe. All right. So after this titration thing, we have now the spectroscopy. Most commonly, you'll see that, like without exception, every year you have these spectrums, yeah, and you should be able to recognize this. For IR spectroscopy, sometimes they ask you write the principles of IR spectroscopy. So basically, they ask you how IR scopy works, not the instrument itself, just the working principle behind that. So for IR, just know these 2 dot points. IR is infrared radiation. It has energy in it. When that infrared falls on a molecule, and those molecule, they have electrons in them. Electrons absorb the radiation and vibrate. So those vibrations are registered, are recognized, and they give different indication by spectrum. Now, this is a principle. Basically, memorize this honestly and know this. Now, the important thing is that you'll be given the spectrum, and you should be able to, in your data book, page 11, you have these values. You have these values. So you need to know that, for example, carbonyl is sharp peak like this at around 700 or 1700. All right. Now, if it is the is coming from let's say esters, it is on the upper range, like between 1720 to 1840. It's still carbonyl, but if the peak is from acid, it is on the low end of the spectrum, like 1680 to 740. So if you see a carbonyl which is at around 1800, all right, and you're comparing between carboxylic acid and ester, so most probably it is ester, not carboxylic. So use this graph here. Similarly, if you have if you are in doubt between aldehyde and ketone, all right, you think, oh, it's ketone, it's aldehyde, ketone, go to this chart. This chart says that if the carbonyl is between 1660 to 1745, is aldehyde. And if it is, let's say you see the carbonyl at 1800 or something, and now you show that it cannot be aldehyde because aldehyde max is 740. So use this graph. Now, some signature peaks. Remember that if you see, very obvious one is OH. So if you see a peak like this, very smooth and broad, and little bit above the medium, like it comes down to 60% or so of the spectrum, that is OH. And OH mean it does not have carbonyl peak. You should not be seeing some peak here. No. If you see, it's not alcohol. All right. If you see here, then it may be alcohol with something else. I'll give you example. Now this is also a smooth peak, but if it was alcohol, first of all, it should go up like that. But if you see another peak like there, all right, and similarly the carbonyl peak is there, but then there is another thing is there that contains OH, but there is also carbonyl, but that is not carboxylic acid. All right, it is something like that. Like there is a carbonyl group, but then there is maybe another CH2, and then there is C, and then OH there on another carbon. So this time, if it's not carboxylic, if it was carboxylic acid, it should look like this. So the difference between OH of carboxylic acid and OH of alcohol is this. Alcohol looks like this, all right, very smooth. The OH of the carboxylic acid look like this. There are like teeth like this, yeah. So this is OH for alcohol, and this is OH of carboxylic acid. All right, you see the difference. So this is OH is coming from carboxylic acid. On top of that, you see this C double bond O peak. So you need to know these signature peaks. Now, again, this is very common for NH2. This is NH2 peak. All right. If you see peak like this, more stronger, and carbonyl, that is amide. Here. So it comes down here. It is from NH2, but then there is carbonyl as well. So 1700 is carbonyl. If NH2 is without carbonyl peak, there's an amino group, and if it is with the carbonyl peak, that is an amide group. All right. Now here you see here, if you see first time, you say that, this is OH from carboxylic acid, but then carboxylic acid is not like this. All right. So if you see peak a carboxylic acid, but it's like that, it means that it is carboxylic acid still, but then in that carboxylic acid there is a carbon-carbon double bond as well. Yeah. So it could be propenoic or something, for example, CH3 and then CH and then double bond CH and then maybe another C then double bond OH. So in this is a type of carboxylic acid where there is a double bond as well. All right. So if the carbonyl peak split into two, because the if you see in the thing here, the carbon-carbon double bond is there and carboxylic acid is there, so they are overlapping. All right. So you see if single like this is only carboxylic acid. Sorry, if you see one peak like this, carboxylic acid, if you peak like this and another peak comes, that is there is a double bond as well. So know these peaks and you should be able to do that. Now mass spectroscopy, the first thing, again, principle, you need to know these. Just memorize that. They may ask you one mark question, what is the principle of mass spectroscopy? The spectra analysis, the most important thing is that this is M over Z, the charge. The ions which are registered by the mass spectrum is only ion, not neutral molecule. If there's a neutral molecule, it cannot be registered by mass spectroscopy. Sometimes there's a question in the exam, they ask you to recognize the fragments, and a student write correct fragment, but then they don't write charge. That's wrong. You need to have a charge, C double bond O, let's say H, to write the charge that is picked by mass spectrum. Otherwise, mass spectrum will not pick up the fragments. Now, the most important thing in the in the mass spectrum is the molecular ion peak. The molecular ion peak is the last peak in the very last or the biggest, you can say, number of the ratio, M over Z ratio. And why it's important? It gives you molecular mass. It gives you molecular. Let's say you using IR, NMR, you think that, oh, my molecule is this, but it doesn't match with the molecular mass, then you have to think again. You have to think that why it's not the correct one. So this is very important, molecular ion peak. And why it's called molecular ion peak? Because the only thing missing from this molecule is one electron, maybe. Yeah. So whatever is the mass of the whole thing. And then the peak, which is 100%, is called base peak. You need to know these terms. They often are there in the multiple choice questions. And other common fragments, how probably they can break, and what is the molar mass of these. Yeah, for example, if they ask you what is the fragment at 29, and you can break in different ways, and what is the fragment at 15. Now you know that carbon is 12, hydrogen, if I add 3, that becomes 15, and there is no other possibility. So that is the fragment which is giving peak at 15. If you have so fragments should be the easily breakable parts of the molecules, and they appear in different M over Z ratios in the spectrum. The one which is 100% is base peak. The one which is the highest number is the molecular ion peak. All right, this gives you very important information. Now H NMR or proton NMR, NMR starts from here. Again, principles, you need to know how it works. Principles. Know the principles of NMR, read these and try to memorize this. These are 1 mark questions commonly asked. What is the principle of NMR? I'm not going to that detail. I'm going into what it means. So in the NMR, let's say you have this NMR and hydrogen NMR, and there are peaks here, peaks here between 0 to 12 for ppm for proton NMR, and 0 to maybe 200 for carbon NMR. So the number of signals in your proton NMR means number of different hydrogen environment. So if I see four signals in proton NMR, it means that I have four different hydrogen environments. All right. Now position of the signal, like it is at 1 or 2, at 3, 5, 6, is the type of hydrogen, like is more polar, less polar, attached to a carbonyl group, attached to a halogen group. What type of hydrogen is that? And then splitting pattern, which is n plus 1. If that one peak split into three, like still one peak, but split into three, the triplet, it tells me that how many hydrogens are there on the next door carbon. All right. And the fourth thing is relative peak area. All right. That gives you intensity. If the peak area is like 1 to 2, it means whatever is this peak is coming from, it is double in the number than this peak. So these are the important things. Number of signals means number of different types of hydrogen. Position of signal, where it is on the spectrum, 1, 2, 3, it means the type of hydrogen. More polar tend to be more down field, like higher number. And splitting pattern, n plus 1. If there are three, like split into three, it means there are four hydrogens on the neighbor. And peak area is intense. How many like intensity mean basically relative number of hydrogen in each environment. Now these terms are sometimes used. You need to know that singlet mean there is a single peak. All right. Doublet mean, of course, the peak split into two, like this. Triplet mean there are three peaks, and normally middle one is the more intense than the other two. So triplet looks like this. And quartet mean there are four peaks, and as they become more in number, they become smaller as well. So maybe 2 looks like this and 2 looks like this. So it looks like this. All right, 4. Now, if there's a singlet, it means that the next door carbons, if there are carbons, they have no hydrogens. All right. So it is possible to have, for example, if you have C double bond O CH3, CH3. So these three hydrogen, basically all six hydrogens are same type. So you will get only one hydrogen signal because there is only one type of hydrogen. And there will be singlet, not doublet, because for these hydrogen, the next door carbon has no hydrogens. Singlet. Now doublet means the next door carbon has only one hydrogen. For example, doublet could be possible from here. If you have CH3 and C hydrogen, and this is maybe, let's say, this one. So maybe for this one, this carbon has one hydrogen, so this will give a doublet singlet. But this carbon may give quartet. Yeah. Now let's see some examples. Chloroethane. Yeah, chloroethane is this. C, and chlorine here. Let's say this is carbon number 1 because function group is number 2. So the carbon number 1 has a neighboring. First of all, there are two types of hydrogens. This type of hydrogen is one type, and this is second type. Wait a second. Sorry, something went wrong. So yeah, for this molecule, chloroethane, this signal, which is coming from these two hydrogens, will split into 4. Yeah. Why? Because the neighboring carbon has 3 hydrogen. So A, which is this one, split into 4. 4, you see, 2 here and third 4. And this signal because the next to a carbon has two hydrogens split into three. So this is splitting pattern. Now, if you look at this, there are three types of hydrogen: type 1, type 2, and type 3. So that's why there are three signals. Now, C has no neighboring carbon or hydrogen. So C has a carbon, but no, on that carbon there is no hydrogen. So that is single. And then B has one side carbon with no hydrogen, other side there are three, so it would be quartet, which is this one. And then A, this is A, because there are two hydrogen next to, so it will split into three. Alright. Carbon and everything is same. In the exam, how would you know that it is carbon and sometime in the first look you can't tell it's carbon and proton and if it is between 0 to 12, it is proton NMR. If it is between 0 to 60, 70 up to 200, that is proton NMR. Everything else is same. In carbon NMR, this just there is no splitting. Yeah. So and different types, each different type of carbon will give you different signal. So if you see there, these are exactly same type of carbons. Yeah. So there's one signal coming from here, and this one carbon is giving a different signal. All right. Now, food molecules, metabolism, those who are doing bio, it's easy for you. That's why I have, what I've done, I have written the important, basically definitions, comparison. I want you to read those. For example, what are coenzymes? Coenzymes are organic molecules that become part of the active site of the enzyme and modify its shape. Alright, a coenzyme may also act as an electron, atom, or molecule carrier. So they are organic molecule. First of all, coenzymes are organic molecule. Cofactors are not. Cofactors are ions or something. So coenzymes, they can or they may carry electrons, atoms, all right, and to facilitate the reactions. And there are different questions I've picked where the students were confused or lost. Why vitamin C dissolves in water but vitamin D does not? Any such question, you have to see your data book. In data book, you have structure of vitamin C and vitamin D. Please look at those structures. Familiarize yourself with the data book. There are so many OH in vitamin C, and there is one or maybe none on the vitamin D. So that's why vitamin C dissolves in water, but vitamin D does not, because the non-polar or hydrophobic part of the vitamin D is way more than the polar part, if there's any. So vitamin C dissolves in water because you can't just say that there are OH groups. So what? If there is a 3-mark question, you say that vitamin C dissolves in water because there are OH groups present, you will not get all 3 marks. You may get 2 or maybe 1. You need to say, so what? So because OH groups are there, they make hydrogen bonds with water, and that's why they dissolve in water. You need to say full, yeah, to get full marks. How to find omega-3 and omega-6 fatty acids? So you need to first, in your answer, identify what is omega carbon. The CH3 side of the fatty acid, which is the other terminal. So one side you have carboxylic acid group, then there are CH2 groups, so many, maybe 17 or so, and then there's CH3 in the end. That carbon is omega carbon. From that carbon, if carbon number 3 has a double bond, that is called omega 3 fatty acid. If carbon 9 has the carbon double bond, that is omega 9, omega 6. Alright, so you need to know this. What is induced fit model? Now, you might know already, but to get full marks, you need to mention all 3 points. I cannot emphasize more. What is induced fit model? You must mention all 3 points. Doesn't matter you use these words or not, but you have to say all these things. So substrate joins at the active site. The enzyme and substrate interact through weak bonds. So first point is that you need to say that substrate and enzymes, they recognize each other, they interact using weak bonds, yeah, and then alter the shape of the active site, which causes the shape of the. So in the first point, basically saying that how active site changes when substrate and when the substrate and active sites, sorry, when the enzyme and substrate approach each other, there are some weak intermolecular forces, and because of those interactions, the shape of the active site changes. You need to say this as a first point. After the reaction is done, everything is done. Because the shape was changed because of the intermolecular forces. Now, when the substrate leaves, um, enzyme leaves, so the active site returns to its original shape. The You have to say this to get the second point. The shape changed, you said in the first point. Now shape comes back to the original. You have to, after the reaction is done, after the catalysis is done, it comes back to its original shape. You have to say that. And third mark you get by saying that enzymes provide an alternate pathway, all right, and lower activation energy. What is denaturation of protein enzyme? Very common question in the food section. You need to have this in mind that denaturation of protein or enzymes is happening only in the secondary and tertiary structure, not in the primary, because denaturation is happening by breaking down of the hydrogen bond or other weak molecular forces into weak intermolecular forces, not by breaking down the covalent bond. If you break down the covalent bond, you hydrolyze the enzyme. But if you break the weak forces, hydrogen bonds and other weak forces, that is denature. All right. So you need to read this, please. When protein is denatured, the secondary and tertiary structures are affected, not the primary structure. Now, normally acids and high temperature affect the hydrogen bonding. All right. Acids can protonate one of the molecules and hence weaken the bond, and high temperature can break the hydrogen bond. So high temperature and pH are the most common one to denature the protein. The bond is disrupted in the tertiary structure, and yeah, it also important that the denaturation process does not necessarily disrupt all the bonds. Even 10%, 20%, 30% bonds are broken, and still the enzyme denatures. This is important. To become denatured, not all the bonds need to break down. Mm. Why saturated fatty acids have higher melting point? Whenever this type of questions come, unsaturated, saturated, remember that because of the double bond, there is a kink. You need to mention that. Because of the double bond in the long carbon chains, there's a kink, and because of the kink, there is no good packing happening. And if there is no good packing, then the bond will break easily. All right, and high melting or low melting point. This question could also be asked with the amylose and amylopectin. They may ask this amylopectin. Which one is low GI? Which one is high GI? Which one is high melting, high boiling? So remember that the amylopectin is branched, all right, and amylose is linear. So in linear, there is stronger the packing. Strongly packing mean they are tightly bonded, more dispersion forces, so they release slowly because the you need to break all the bonds. And amylopectin, because of the branches, the packing is not good. When the packing is not good, they can be broken down easily and more available in the blood as a sugar. So amylose, they are low GI. Amylopectin, the branched one is high GI because the bonds are not stronger, packing is not good, they easily break down. So I was talking about saturated fatty acid and unsaturated fatty. Fatty acid, they have carbon-carbon double bond. That carbon-carbon double bond causes kink, and because of that kink, the packing is not good. All right. So read this. Importance of the tertiary structure. Sometimes this question is asked, why the tertiary structure is important? Because tertiary structure is in certain shape, and shapes are very important in enzymes, because the substrate, the lock and key model is based on, if you have a lock, the shape of the key is very important. If the key is not correctly cut, you can't open the lock. All right. Same is for the tertiary structure. There's certain shape for certain function. You change the shape, you change, basically that enzyme is not going to work for that function. So you need to read this, and you know that why it's important. Why energy from the food molecule is released less than the value? Because uh, the energy is lost during the process. Yeah, energy loss is very important. Some food is not fully digested for some reason. What is rancidity? How unsaturated fatty acids become rancid faster? So rancidity is basically reaction with the fatty acids or fats. Yeah. Carbon-carbon double bond, they are more reactive. Remember, we learned in the reactions that alkanes, they only do one type of reaction, the combustion or the substitution. But alkene, you can add anything on it, H2, H2O, HCl. So alkene double bond, the carbon-carbon double bond is more reactive. So that's why unsaturated fatty acids are more common. They become rancid faster. All right. That's why you see that mostly oils are put in the dark, and sometimes if you see olive oil in the coals of woli, you see that they are in the green bottles, and they ask you in the instructions that put it away from light, and always keep the lid closed. Why? Because air and light both can initiate the reactions. Any reaction, oxidation can happen, and that's when the oil become rancid. Read this. Aspartame is sugar or not? This is all the artificial sweeteners. They are not carbohydrates. They are sweeter, and maybe up to 200 times more sweeter than the normal sugar, but they are not carbohydrate. They don't increase the sugar level in the blood. All right. So yeah, no, it's not a sugar. Sugar is considered which something which breaks down, hydrolyzes into smaller monomers, which are glucose or fructose or something. But this is not carb. This is not sugar. All right. What is this? It is a methyl ester of a dipeptide. It is hydrolyzed into two amino acids and alcohol. All right. So this is not carbohydrate. This is not sugar. And it is much sweeter. In 1 gram, it has 17 kilojoules, same energy. But the thing is that it is 200 times more sweeter. So if you add one, maybe teaspoon of sugar to make something sweeter, remember that 200 times less of aspartame is required to have the same sweetness. All right. It does not raise blood sugar because there's no carb. Now, another thing, when you are asked to encircle the name and the bond in a structure, you need to remember that you do it correctly. Now, VCEE accepts both. If you ideally you should pick this is this is the bond, all right, a peptide bond or amide bond. But if you're asked to circle the amide, you need to pick all one, two, three, four, all four, preferably all four atoms. But if you just pick these two as well, they'll accept it. But preferably pick all four, but not three. Try to pick all four. So similarly, the bond is here, but you are picking this one, yeah, for dipeptide bond, amide bond. For ester, for example, encircle it. Many students, they encircle the correct one, but in the answer, they write that amide and ester in the answer. Now, how assessors know that if you don't write it here, which one is amide and which one is amide bond in your head? How the assessor knows? All right. So when you encircle something, it's best to write on top of that the name. All right, not write in the given space. Just in the given space, say that see the diagram. This is what I was telling you before. The hydrolysis is when there's amino acid and the covalent bond, amino acid and covalent bond, amino acid and covalent bond, and that's how it becomes protein. And then there is another amino acid and another amino acid, and there is a weak bond, maybe a hydrogen bond. If you break this bond, the weaker bond, using low pH or high pH or high temperature, it denatures the structure. But if you break this bond, that is hydrolysis. All right, hydrolysis is the breakdown of primary structure, covalent bonds, and denatures is when you break down the tertiary structures. All right. Now calorimetry is basically you need to calibrate the calorimeter before you start using it, and that is called calibration factor. If you have a calorimeter, you need to find out how much in for calibration factor you need to use the energy here. You know that E is equals to V I N T. So you need to use energy here. Now that energy can come from two pathways. Through electric pathway, like you electrically heat the water inside. All right. If the energy you calculate using the electric heater, then voltage, current, and time is required to calculate energy. Another way is that you do a chemical reaction, and that chemical reaction produce the energy, and use that one. Then you use this E is equals to moles times the heat of combustion for that reaction. So energy could have two formulas depending. It is the energy is being produced through the chemical reaction or through the heating electric heater. All right. Once you have the energy, CF can be found. This CF calibration factor is E divided by change in temperature. Now this E could be any of the E you can use depending on the question. So yes, use this formula to calculate calibration factor, and calibration factor times delta time change in temperature could give you energy. So some of these formulas are given in your data book, other you have to find out. You can rearrange this one. Q is equals to MC, delta T is also used here. Now let's see some question here. Calculate the change in heat or heat energy from sodium dissolving this. So they have given you the chemical reaction. 100 ml of water is given to you, 5 grams sodium dropped in the raised temperature. So this heat change in energy is coming from not electric heater, by a chemical reaction. All right. So specific heat of water is given in your data book. So use that one. In this case, Q is equals to MC delta T. Use all the values to find Q, which is in this case energy E. And once you have Q, use this formula and put that Q or energy here and find the change in temperature. So there are more questions. I hope you practice and you can be very good with these type of questions. Remember boys, one question every year between 10 marks to 13 marks maybe is from experiments. All right, they give you an experiment where they give you procedure, data, everything, all the tables are given. They assess your ability to analyze the data and make conclusions and everything. That question is easier. Why? Because you have done these you've learned these experimental writing hypotheses, independent, dependent variable in psych and biology, in chemistry. So first two or three questions are normally what is the independent variable, dependent variable. So it's easy to tell. The independent variable is the one which the experimenter is manipulating, which is controlling. He is controlling. Is independent. Dependent is the one which you're measuring, which you're trying to learn. Yeah. So and hypothesis, just find the relationship between dependent and independent variable and make an hypothesis like I it is hypothesized that the use of fine powdered calcium carbonate will have faster rate of reaction than the calcium carbonate used as pellets, something like that. Yeah. So you have dependent, independent variable, um, and and then there should be a direction in the hypothesis. What happens if and then should be there. And most commonly, they may ask you some questions like about systematic error or random error in that type of question. So you need to know the difference between systematic error and random error. Systematic error, the name shows that it is error in the system. If you're weighing something and your balance is out of order, that is systematic error. Every time you weigh, you'll have the same problem. All right. So systematic error cannot be fixed unless you fix the system. So are consistent, repeatable errors associated with the faulty equipment. Now, repeating a procedure. If you think that by repeating you will remove the systematic error, no. Well, this is normally asked question. If there is problem in the data, can by repeating the experiment, will the error will be removed? If it is fault in the instrument, no, it cannot be. All right, so you need to know that. Random. Remember another thing. Systematic error, if it is there, your results will not be accurate. If random error is there, your precision is affected. All right, you need to know this. And there are more differences, how it can be corrected. Read this. Yeah, with this, I have completed the quick revision of part 2 of Unit 4. So watch all three, and before you go next day for the exam, watch this again. I hope I'll give you the hard copies in the class as well for these notes. And if you have any question, I'll be available in the school on whole next week. You can come anytime. We can have another Zoom meeting to address your questions. All right. I wish you good luck with your exam, and I hope you have really amazing ATA score and really good score with your chemistry. Good luck, boys.